All right. So, folks, notes copies out there, please, and your title. Chapter 19, the first of our electricity chapters, is your static electricity. All right. So one of nature's finest examples there of static electricity, on a picture on the slide. What is it? Lightning. So a build-up of static electricity in clouds causes a thunderstorm. You have your thunder and your lightning. And why does the lightning travel from the cloud in those shapes back to Earth? What's it trying to do? You've all seen lightning at some stage. What's it trying to do? What's built up in the clouds? What's trying to move from where to where? Do you know? So it's a static charge building up in the clouds and it wants to move to ground. So have you heard of grounding something or earthing something? So charge, when it would build up, would try and go to ground. Do you ever get a shock off the car door? Trolley in the supermarket? So there's a build-up of static and it will go through you. You're a conductor and it will go to ground and give you a bit of a shock. So static electricity there in a big build-up would cause your lightning. So what does lightning do when it hears a joke? What does lightning do when it hears a joke? It cracks up. Right. We'll move into the starting point here. We're going to look at conductors and insulators. He had this back in junior cert, different materials that would either conduct or insulate, and he probably had it in terms of heat as well, conducting heat or being an insulator. We're going to look at how an object becomes charged and with different types of charges, positives and negatives, how they work together or affect each other. We're going to look at some real life static problems or applying it to real life dangers and things like that, alright? So starting activity there to get you thinking, can you name something that's a conductor and something that's an insulator? Any material item? Top of your heads. Think of it in terms of heat, maybe. Metal, which one is that? And what happens when metal is heated up? It's hot. So that heat is moving through the molecules. Whereas you're cooking your pot of soup, you don't want to burn your hand. You're not going to stir with a metal spoon, you're going to stir with what? Wood, okay? So the you wouldn't feel the heat then coming through the wooden spoon. Okay. Which one will cause a build-up of static? Will the conductor or the insulator cause a build-up of static, and why? Have a chat to each other there. Which will cause a build-up? How many votes for the conductor will build up the static? How many votes for the insulator will build it up? More votes there for the insulator. Why are we going for insulator?
Because the conductor will just allow the electricity to flow through.
Yeah, it'll allow the charge to move through it and move away, whereas on the insulator, it won't allow it to go through it, so it'll build up. Yeah, spot on. So they prevent the electricity from flowing away. So if we think of the lightning case, you might have seen on tall buildings a copper rod on the side of a tall building or spires of churches. That is to attract the static in a thunderstorm and allow it to travel through it and ground it, as opposed to it hitting the building and damaging the building. Alright. So just one very simple everyday example there. Okay, so this you know from back in Junior Cert. What is an electrical conductor? Defining it here is a substance through which electric charge can flow. We also would have looked at it in terms of heat, so that energy passing from atom to atom. Here it's electric charge passing from atom to atom and flowing through it. And common examples there, any type of metal, silver, copper, aluminium, they're all conductors. Water is a conductor. The human body, your skin, we are conductors, poor conductors, but we're conductors, and the ground. Alright, so I'm going to get you to note your definition and take two examples. Okay, recording is starting there again. Sorry folks, catching up at home, we just spoke about the metal used in wiring being copper, why it's used. It's a good conductor, it is ductile or bendy, and it's relatively cheap compared to, for example, silver. Okay, so back to folks in the room here now again. The electrical insulator there, we described it a while ago and talked about it. So it's the opposite definition to the conductor. An electrical insulator is a substance through which electric charge cannot flow. And an example, we came up with wood there a second ago. Glass, plastic, rubber, air is an electrical insulator as well. So again here, just note your definition and two examples there of the insulators. So in an insulator, the charge that is moving is a negative charge in an atom. Can anyone tell me what the negative charge? It's a subatomic particle within an atom. There's a positive charge, a negative charge, and a neutral charge. What did we call the negative one back in Junior Cert? Good, the electrons. So electrons will move quite easily or freely through metal conductor. They won't move as easily through an insulator. All right, they can't easily move from one atom to another. Okay, you are going to try a few static electricity home experiments here now. Plastic pen. You might have played this game back in primary school. Rubbing the outside of the plastic pen against a woolly jumper and trying to pick up little pieces of paper. When I'm talking about a plastic pen, these ones, the big clear pens, if you have one of them in your pencil case, you are trying to build up static by rubbing it against a woolly jumper and then rip up a few pieces of paper and have them on the desk, and it should attract them when there's a build-up of static. And the second experiment, if you're looking for a pen, I have loads of them here, you can borrow. The second one you can try is with the water in the tap. So you can take one of these rods, a polythene rod. I'm not sure which one is polythene. Some of them are acetate, some of them are polythene. So you might try a couple of the different plastic rods here. Again, either with the woolly cloth here, filling up the static, or against your jumper. Turn on the tap, and when you bring the rod near the tap, it will cause the stream of water to move. So will it attract to the rod, or will the rod push it away? That's what you're trying to figure out. Alright, I'm going to stop the recording for a second. You're going to try that. Okay. So we saw there forces. We saw things being attracted when they had a build-up charge. Are you alright? So what are you doing when you are rubbing the pen off the woolly jumper or the rod? What are you doing in terms of the motion? What do you call that motion? Rubbing one thing against the other, a build-up of heat, a build-up of charge. Friction. So you're causing friction, you're causing a movement of things, and what's happening there with that friction is you're moving negative charges. You're moving negative charges, okay? So there's a series in chemistry called the triboelectric series. It tells you which materials have greater tendency to gain or lose negative charges. Some are better than others. So what are these negative charges there? They are the electrons, okay? So into the atom, back to junior cert science here again, we have everything is made up of atoms. In the centre of the atom, we have the nucleus, and there are two subatomic particles that live in the nucleus. The protons, they're positively charged. The neutrons live in the nucleus as well. And then in orbits or shells or clouds surrounding that centre nucleus, we have those negatively charged electrons orbiting, okay? So they are opposite charges. You've probably heard of the term opposites attract. Opposites attract. So the electrons are kept in orbit around the nucleus because the negative electrons are attracted to the positive protons in the centre. Alright. If we had all protons, the protons would repel the protons. Okay? So I'm going to write now on the side of the board. Key pointers. I'm going to write up. Opposites attract. Opposites attract. And we have this like charges repel. So if they're both protons, both positives, they repel each other. Unlike charges attract. Alright. So I just want you, for the moment, to take down opposites attract. Opposites attract, e.g. electron attracted to proton. Opposites attract, negative electron attracted to positive proton. Alright. So the forces of attraction here and repulsion, if they attract or repel, we call these now electrostatic forces. So we're used to forces in terms of mechanics. Now these forces are going to exist in terms of electricity. So they're electrostatic forces. If particles exert electrostatic forces on each other, they are charged and we call them electrically charged, alright? So electrons are always going to be negatively charged, protons are always going to be positively charged. And if the amount of positive versus negative in an atom overall balances each other out, we call that electrically neutral. So it's electrically neutral, alright? And most atoms are electrically neutral unless they undergo something else and become something called an ion. We'll get to that later. So if the substance picked up extra electrons, what's its overall charge then? If it picks up extra electrons, what's its overall charge? Negative, yeah. If it loses those electrons, it loses some of the negatives and it becomes overall positively charged, okay? You would have had this back in junior cert science as well. Okay, so we are going to charge up some rods now. So the different rods here, they're made of different materials, polythene, acetate, different materials. So this one, they're the acetate rod. You are going to use a woolly cloth or your jumpers again. And the other rod type is polythene. I don't know which one is which, so you're going to experiment with both in a minute. We're going to move electrons, so you're either moving it from the cloth to the rod or you're moving it from the rod to the cloth. So this is an animation here. With the acetate, the electrons will move off the rod and over onto the woolly cloth, so the rod ends up being overall left with more positives, positively charged. The cloth then gains those electrons, the cloth will become negatively charged. Polythene then, on the other hand, rubbing with the cloth there, the electrons move off the cloth and they're attracted to the rod. So there's more negatives there on the rod. Your cloth will be positively charged and the rod will be negatively charged, all right? So we are going to run an experiment in a minute where you have two different types of rod and you're going to see if one gets charged overall positive, the other one overall negative, and we bring them near each other. What might happen? They'll attract, they should, opposites attract. And then you can do an experiment taking two of the same type, charge them both positively or charge them both negatively, and if we bring them together, like charges, well, both negatives should repel or push away from each other. Alright, so we're going to try it here in about 5 minutes. We need to know the two types, very simple. The two types of electric charge are positive charge and negative charge. And do they attract or repel forces on each other? Both. So the like charges repel and unlike charges attract there. So just under a heading of electric charge, take down what's in the yellow boxes. Positive charge and negative charge. Like charges repel, unlike charges attract. So a minute ago there, where you charged a rod and brought it near the stream of water, it was repelling the water away from it. Was it? Or was it attracting? I can't remember. Was the water being attracted to the rod or being pushed away? Both. So different plastics did different things. Yeah, interesting. Yeah, so the one that was probably the same charges were trying to repel each other, and if there was a build-up of a different charge, it was attracting. Are we okay? I'm going to move it on to the demonstration experiment. We're going to talk about it, take a few notes, and then you're going to do it. Or try to do it at least. So you could be asked to describe, using a diagram, how to show force between electric charges in the lab. So this is taking two rods, two plastic rods. You rub those rods, say polythene, with your woolen cloth. You would place one of them hanging from a paper stirrup in a retort stand, and you would bring the second charged rod near the first one but not touching, you should observe that the rods would repel each other, showing a force between charged bodies. So because they're the same charges there, they would repel each other. Okay? So you need this diagram in your notes with the title, and you need a few bullet points. The main point here is that like charges will repel. So like charges will repel each other. It's the main point. You don't need everything here step by step. You do need your diagram and the observation or conclusion. The like charges will repel, and that tells us that there is a force between charged bodies. The last point there, that's like with the diagram. If we then take two different rods, so you charge a polythene rod negatively, you charge a acetate rod positively, same setup, one hanging in the retort stand, the other rod being brought towards it, you will see there that the opposite charges should attract each other. So same conclusion here, that there is a force between the charged bodies. When they're oppositely charged, they attract. Okay? You don't need a second diagram as such, but you might take a note that you would have two different plastics here with opposite charges, showing charge attraction to each other. Okay? When you have it taken down here, you're going to try it. You are going to take a couple of each rod. You're going to take two of the same types and charge them. You're going to take two opposite types and charge them, and see can you get them to attract or repel each other in either case. Okay, so eyes up on the board there now again. We're going to talk about the atomic nature of electric charge. So I spoke earlier, if it gains more electrons, it gains more negatives, we'd say it is negatively charged. If it is positively charged, it has lost those electrons. So the only particle that actually moves from an object or to another object is the electrons. So protons stay in place, but if extra electrons come into the region, there's more negatives than positives. Does that make sense? So here we have a conductor, metal conductor, and a charged rod. So on that metal conductor, it will have a balance of positives and negatives. If we bring a charged negative rod towards it but not touching it, your like charges will repel. It's going to move those electrons away from the negatively charged rod over to the other side of the conductor. That's what's happening there. Okay? So just one quick note there, the white writing. If an object is negatively charged, it has gained electrons. If an object is overall positively charged, it means it has lost electrons. Okay? So here I have a metal conductor and I have a plastic handle on it. I'm going to charge it in a minute, theoretically. Why does it have a plastic handle?
So that your body doesn't take the energy.
Yeah, so that my body in between, if I was touching the metal, would act as a conductor between the charged metal and the ground, and the charge would flow through me. And you'll get static electric shock. Alright. There's a lot here in this slide, I'm going to talk through it. If we wanted to charge our metal conductor here, we can bring the negatively charged plastic rod towards it. The electrons, we call them free electrons, they're free to move about in the metal. They will get repelled or pushed across to the opposite end of the metal. It'll appear on one side as more negatives, the other side then will be left over with the positives. If we remove that charged rod, they'll just move back to where they had come from. They'll redistribute those electrons back again, alright? So we are if we're putting a charge on a metal, we're inducing a charge. So you might have heard of the term induce or induction. Anyone have an induction device in their homes for making dinner? Anyone? You heard of an induction hob? Oh, you're nodding, yeah. So it induces a high temperature or heat to cook the food quickly. Induced labour. They would give a woman in labour drugs to bring on the labour or make something happen. So that term induction. We're going to talk about here in terms of charging by induction. Alright. So induction is the process of bringing something about or giving rise to something. So if we want to cause a total single extra charge on a conductor, we can charge by induction. So here, if we have two conductors next to each other, bring a charged rod up to it, what's it going to do to the left-hand sphere? We're bringing the charged negative rod up to the left sphere. What's it going to do? They're touching each other here. This is the second diagram at the top right there. We're bringing charged negative rod up next to this guy. This has both positives and negatives starting off. What's it doing?
The electrons will go into the firewall.
Yeah. So the electrons will leave the left-hand sphere, move across to, because it's being repelled by that negative rod, over to the right sphere. Then, if we keep the rod next to it and we separate them, all the electrons have moved across here, haven't they? So this is going to have an overall more negative charge, and this one is going to have an overall more positive charge. Right. So we can charge things by induction here. This one I'm going to get you to take a note of in a minute. If we were to do it for a single conductor and we bring ourselves into the equation in terms of grounding something, you can bring, first top left diagram, bring the charged negative rod up next to the sphere. That will push the negative electrons over toward the right hand side of the sphere. If you then keep the rod in place and touch the sphere, what's going to happen to those electrons on the right hand side? Yeah. So you're grounding it, you're a conductor, aren't you? So those electrons are going to move through you back down to Earth. We're taking them away from the sphere, aren't we? They've been removed. So next step then, keeping the rod in place, if you remove that earthing connection, you remove your finger and then remove the rod, we're left with an overall just those positive protons left. Okay? If you wanted to charge it the opposite way around, you wanted to leave an overall negative charge, you'd start off with a positively charged rod. You don't need to know both, you need to know one. So this diagram here, 4 steps. Step 1, top left, bringing the charge rod near it. Step 2, earthing it. Step 3, keeping the rod in place, removing the earth. And step 4, you're left with the overall positive charge. So you need a diagram 1, 2, 3 and 4, and you need the steps there underneath as well. If you were asked how to charge an object positively by induction. They do like to ask this one a lot in exams. Okay, so the device there in front of you in the desk is what we call a gold leaf electroscope. This is a very original, old-fashioned one I have here at the top. And you have a metal plate at the top. My one here then has a bit of rubber insulator. Your ones have cork insulator. Then you have a long metal rod going down to the centre, and you should have a bit of gold foil attached onto that alongside it, a gold leaf. You have a casing then, so it's going to be air, there's going to be glass there surrounding it, and we have a window of glass so we can see what's happening. So this is called a gold leaf electroscope. You can charge it, so like we did a while ago, charging by induction. You can charge the gold leaf by induction, and then it can be used to test whether a charge is positive or negative. It can detect charge, and it can test if something is a conductor or an insulator. It has been asked in an exam before to draw and label a gold leaf electroscope. I'm not going to get you to do that today, but be aware that it can be asked. And they'll be looking for a few of the key parts: the metal cap, the insulator in between, the metal rod and the gold leaf, and then the surrounds of it being the metal case and the glass window. Alright. So this one here. So a couple of bullet points here. Why does the gold leaf diverge when the negatively charged rod is brought towards it, the metal cap? Because the negative charge repels the electrons down the rod, like charges are building up at the end, and those like charges are repelling each other, diverging and moving the leaf outwards. Questions? Are you okay? Yeah? So just a few bullet points there. If you were asked, why does the leaf diverge? When you come in as the human then, and you ground it, the leaf will collapse. But then, when you take that grounding away, and you're left with the overall positive charges again, the leaf will move back out again. We're going to try it next week. They don't work very well, but we can try it. The unit of charge we're going to come across and be using now the next few classes is something called the coulomb. Coulomb of charge is one single unit, and we have a law called Coulomb's law that we can mathematically work out how much charge exists between two different bodies, or how much force is there, and so on. And then next Thursday in here as well, we're going to be looking at the Van der Graaf generator. So we'll do some experiments there as well, where we'll have a high build-up of charge and do just some demonstrations on that. It's pretty cool. Okay. So this concept here, same concept as the spheres a while ago. Bringing the negative charge towards it, grounding it, then the electrons are flowing through you back to ground. We're left with just the positives. Remove that grounding connection, remove your rod, and you're left with just your positives again. Alright. So you could be asked the sphere method or the gold leaf electroscope method. You can use either of them to show something charging by induction. I'm going to go back to the diagram a second and just get you to take a couple of bullet points from the diagram. For your homework, can you read through pages 227 to 229? That's introducing Coulomb's law. There's some example problems there on using the formula, and I'm going to get you to try 4 of the questions, alright? So between now and Tuesday, we'll read through those few pages, study the sample problems, and give those 4 questions a go then, alright?